So good afternoon, everyone. Before we go live, visit is sponsored by OTREC. And along with Jennifer Dill, Chris Monsieur, and John Glebe, we organized this Friday seminar, and I think we've had almost 160 of these seminars, and about 120 of them are available on the web, as will this one in a few days. I don't want to give an exhaustive introduction of our speaker, but he is the J.R. East Professor of Civil and Environmental Engineering and Engineering Systems at MIT. People refer to Joe as the father of ITS. I'm not sure if he admits to that, but he's been involved for many years in the development of our current and hopefully our future ITS program in the United States. So without further ado, I'll turn it over to Joe.
Well, Rob, thank you very much. It's a pleasure to be here with you at Portland State University, and whoever else is listening out there, I'm pleased to have you as part of the audience. I'm going to talk today about my view of where the field of transportation is going, and some of it may resonate with you, and other parts of it you may find more controversial. And if we can have some time for questions at the end, perhaps that would be of value to. Certainly to me, and perhaps to the other folks here. Rob is too kind in terms of attributing me the title of the father of ITS. This is, of course, an area in which I've done a lot of work, but so have a number of other people. And while I was fortunate enough to be in at the beginning, this is a field that's expanded, grown, morphed in a variety of ways. We'll touch briefly on some ITS concepts as we proceed through this discussion. Had the opportunity this morning to visit the ITS laboratory here at Portland State and meet some faculty and students who are interested in the area from a research perspective, and it sounds to me as though you've got some very valuable activity going on in the ITS area. The The topic of my discussion today is where transportation is going, transportation in the CLIOS System Era. To many of you, the term CLIOS may be a very new one, and I'll say a few words about what I mean by the CLIOS concept. And then I will give you some illustrations of a CLIOS system, and then talk about the evolution of transportation into what I now postulate is the CLIOS System Era, and what kinds of thinking we have to engage in order to be effective participants in that as transportation professionals. Whoops. No, yes. I'm sorry, it just took its time. There we go. As kind of an introduction to what I want to say is I want to begin by giving you a sense of the evolution of the broader field of engineering, and to argue that we are moving beyond a narrow focus on what I might call engineering science into a broader perspective on in what I call engineering systems. Now, engineering science, I just saw my picture on the video, a bit disconcerting to see what I'm looking like to all these folks out in cyberspace. The field of engineering science back in the 1940s and 1950s really revolutionized the study of engineering. Engineering to that point in time had been, one could characterize it as largely empirical in notion, and the idea that we should build the field of engineering on fundamental scientific principles was new and innovative back in that period of time, the World War II period, the post-World War II period. And it had, and I was educated back at that time as an undergraduate and also as a graduate student at MIT. And the notion here was that we ought to build the foundations of engineering on fundamental physics and mathematics and chemistry, as a strong quantitative base for what engineering was about. And this has had a great deal of value in the maturing and intellectualizing, to a certain extent, the field of engineering as it exists both in professional practice and as it exists in academia. And this has had a tremendous amount of value in terms of the engineering field. But while it has been valuable, it's also created a very microscopic view of what the field of engineering is about. I often talk about a vertical versus a horizontal orientation in the way in which one thinks about engineering problem solving. And the engineering science perspective tends to be intensely vertical. It tends to be, if you will, reductionist in the way we look at engineering problems, drilling down very deeply to fundamentals, an important way of thinking about engineering, but perhaps an incomplete way of thinking about engineering. And we have seen over the last decade or so the notion of engineering systems as a more integrative, more horizontal way, a more interdisciplinary way of thinking about how systems in their entirety behave, as opposed to the more reductionist vertical engineering science perspective. Now, that's not to say that engineering science isn't valuable, and it isn't to say it doesn't have a future, because of course it has a critical future in what we do in engineering. But we're arguing at places like MIT and a number of other places around the country that a more integrative engineering systems perspective is important as well as we think about studying what we call critical contemporary issues, issues that tend to be inherently interdisciplinary or integrative in nature. And I'm going to argue that transportation is one such field. And I'm going to argue that in the future we're going to see more and more attention paid to this more integrative perspective. This doesn't move very quickly when you hit the button. Oh, there it goes. It takes a while, so I'll have to learn to pause. Otherwise, I'll be going back and forth all afternoon. At MIT, we argue that the field of engineering systems exists at the interface of management, social science, and engineering, and it's in that portion of the Venn diagram where we have the field of engineering systems. And we've established at MIT back in 1999, late 1998 to be technically correct, the Engineering Systems Division, which has as its focus the integration of faculty members around MIT with this systems point of view, and that come together as an intellectual community thinking about the systems approach to solving a variety of issues, working on a variety of issues, in my particular case, transportation. So that's kind of where we sit in terms of the intellectual underpinnings of what we're thinking about as a systems approach. And with that, let me move into this CLIOS idea, because I'm sure you've all been waiting with bated breath to discover what CLIOS actually stands for. CLIOS complex is an adjective, a collective adjective, which modifies the noun systems. We talk about CLIOS systems, where CLIOS systems, we argue, are complex. They are large in scale, either in the geographic sense or in the impact sense. They are interconnected to other socio-technical systems. They are open in the sense that we consider social, economic, political aspects in thinking about them. And they are socio-technical. That is, they have an important technology at their core, but we also must recognize the social implications of the kinds of decisions we make as one tries to understand or even design a CLIOS system. This is a coinage we came up with some years ago, perhaps 7 or 8 years ago now, and we have been working in my research group on CLIOS systems characterizations, and indeed in our research have developed a process called, surprise, surprise, the CLIOS process, that is intended to come up with an organized way of studying these kinds of CLIOS systems. So I'm going to try and give you some sense of examples of these CLIOS systems and what it means for us to be working in this particular milieu as we proceed through this talk. So let me try and define some of these terms for you. The first, the C in CLIOS, stands for complex, and I will suggest to you that there are a number of ways in which a system can be complex. Indeed, I wrote a paper back around 7 years ago now that simply collect something like 30 different definitions of the term complexity, and I suspect one could go onward and onward in those definitions. The computer scientists have a particular perspective. The management scientists have a particular perspective. One could go on and on simply talking about complexity. I don't propose to do that here today, but certainly there are many definitions that go beyond Webster's in terms of what complexity means. For the purpose of our discussions here today, I've reduced it to 4. I talk about structural, behavioral, evaluative, and nested complexity as important in the context that we're concerned with, transportation and related systems. Structural complexity is simply a measure of the number of components that make up our system. Sometimes we talk about subsystems or elements making up systems, but the number of components in a system and the network of interconnections between them serve to characterize the structural complexity that exists. And that tends to lead to, that's an internally generated perspective on complexity. You simply look at it and say this is very complicated in terms of the interconnections that it has. And it makes understanding that system often very difficult, and it makes changing those kinds of systems particularly difficult. The best example that we have, that I have of structural complexity, is the idea of a structurally complex series of computer programs. Anyone who's written a computer program with more than 2 or 3 moving parts or subroutines knows that going in and changing one of those parts can lead a computer program, a computer system that's been working beautifully for years, to collapse. We go in and change one format statement for the way in which we want the outputs displayed, and all of a sudden, for reasons we can't possibly fathom, the system of programs doesn't work at all. So that's a manifestation of structural complexity. Behavioral complexity is a more externally view of what we mean by complexity. The fact that our ability to predict the behavior, the external behavior of a system, the behavior that emerges from the way in which the system fits together is very, very difficult. So behavioral complexity says that we don't really know how a CLIOS system is going to behave because of the complexity that exists on a structural level. So you talk about emergent behavior. Emergent behavior can be positive or negative. We may get emergent behaviors that result from putting system components together that give us a bang for the buck that we didn't realize we were going to get. More often, it seems to me that behavioral complexity gives us emergent behavior that's entirely negative, that we didn't understand we were going to get when we put together a complex system. Evaluative complexity gets more into the stakeholder perspective on complexity. That is, evaluative complexity reflects the fact that different stakeholders or different decision makers may view the performance of the system in very, very different ways. We talked about performance with the ITS students and faculty immediately before this meeting. And here I'd suggest that evaluative complexity is particularly important to us in transportation, because it means that even if we were able to solve questions of behavioral complexity, that is, we were able to make good predictions of how a system would behave, we would be unable to necessarily reach a decision on whether we should operate the system in a particular way, because different stakeholders might have very different points of view on whether that behavior was good, bad, or indifferent. So if we're thinking of adding runway infrastructure to Logan International Airport, you could imagine that even if we were able to predict with certainty what the implications of adding that runway infrastructure would be, and I hasten to say that's a non-trivial problem to be able to make that prediction with certainty from the point of view of the operation of Logan as well as the interconnections that Logan has with other inputs. But wish that problem away and say we're able to predict with precision what will happen if we add the infrastructure. You may have quite different points of view on whether it's a good idea to do it, because if you live in the suburbs and the efficiency of Logan is important if you travel a lot, you may have the view that why not add that infrastructure, but if you live in East Boston in the immediate environment of the airport and you've already been battered and bruised by the noise and the related ground transportation, you might say maybe the pain of some of this additional capacity could be borne by someone other than me, and perhaps this additional runway infrastructure doesn't make sense. So those different points of view about system performance are evaluative complexity. Even if we know what how the system will perform, doesn't mean that we have an answer about whether the change that makes that system perform in that way, whether we should go forward in doing that. And finally, in this short list of complexity, we have what I call nested complexity. The idea that we have a very complex physical domain. An airport, again, and using that example, is physically very, very complex. We've got vehicles, airplanes, we've got people arriving at that airport from all over the place by various modes. We've got the interaction of that airport with other airports on the national system. Physically, we've got a very complex issue, but we also have what I call the institutional domain or the institutional sphere, the organizations, both formal and informal, that relate to the operation of that physical domain, in which the physical domain is encapsulated. And I have a picture that shows the physical system, or a layer of the physical system, embedded within a policy system, or an institutional system is a term we use there as well. And this leads to what we call nested complexity, that even if we know how we want to make changes in the physical domain, we're often faced with doing it with an institutional structure that may be counterproductive from the point of view of making those changes. So in our work, for example, in Mexico City, and we chatted briefly about that in the earlier session as well, simply knowing that you have some changes you'd like to make with enhanced public transportation in order to ameliorate some of the air quality effects, and getting that done within the complex institutional sphere, if you will, that exists in Mexico City, these are two quite different things. So we deal with all these kinds of complexity. We deal with internally based structural complexity, externally based behavioral complexity, evaluative complexity reflecting the fact that different stakeholders have different points of view, and nested complexity reflecting the fact that you've got institutions as well as physical systems, and those institutions may not work terribly well as one tries to deploy changes on the physical domain. I have to, in aside, say I saw John Mackler just quickly pass up an opportunity to look at my text. Of course, he's memorized every golden word from his time at MIT, so I know he thought it was more important that other stakeholders have a chance to look at it rather than dominating that. I couldn't resist that, John. I'm sorry. So let's talk a little bit about a particular CLIOS system, and to try to illustrate briefly some of the ideas that we bring to the table in terms of how these abstract concepts relate to a particular one. And the CLIOS system that I choose for this discussion is one that's been in the public eye off and on for 20 years, illustrating the difficulties in actually getting things done in the real world. And this CLIOS system deals with transporting spent nuclear fuel. As people here may or may not know, you've got nuclear power plants spread all over the country, each generating SNF, or spent nuclear fuel, a highly toxic radioactive substance that no one wants to be around for a variety of reasons. And the idea that's been on the table, and indeed, interestingly, the law of the land, is that we will transport that spent nuclear fuel from these 130 some odd nuclear sites around the country to a repository in Yucca Mountain, Nevada, about 100 miles, I guess it is, northwest of Las Vegas, Nevada. And the notion of doing this has turned out to be a tough nut, very difficult to solve. This system has complexity of all the sorts that we've described before. It's certainly has the characteristics of us finding it difficult to predict, if we deploy a system to move that spent nuclear fuel, how it will in fact perform. It certainly has evaluative complexity, depending upon whether you live in Nevada, where, for reasons that are probably fairly clear, people are very concerned about the movement of everybody's nuclear waste from around the continental United States to their sovereign state, or whether you live near a nuclear power plant in Maine, where you're concerned about the continuing accumulation of spent nuclear fuel on site. Evaluative complexity, you may have very different points of view on what the strategy for handling this SNF is likely to be. And we have nested complexity because the institutions, both public and private, that we have to deal with in getting a system deployed that will allow the safe and efficient movement of these materials is very institutionally complex. We have private sector organizations like railroad companies and trucking companies. We have state departments of transportation. We have the Department of Energy. We have the Nuclear Regulatory Commission. Actually putting together the institutional machinery to make this happen is extraordinarily difficult. I might comment, I'm teaching an undergraduate class right now, a junior level class at MIT. That's a case studies class. It's called Engineering System Design, and we are working on a class-wide project for dealing with, coming up with what I call strategic alternatives for dealing with the question of spent nuclear fuel, which has, of course, become a much more current issue, an important issue in the last several years, as we begin to understand the impact of carbon-based energy sources on global climate change. And the United States is finally starting to understand that this is not some scientific mirage, but actually has some substance behind it. And nuclear energy, previously very strongly resisted by environmentalists because of some of the potential negative environmental impacts, see 3 Mile Island, see Chernobyl as examples, are now becoming advocates. It's interesting to see how the perspectives of stakeholders change. So evaluative complexity can change over time. All of a sudden, the fact that nuclear energy plausibly could be a relatively carbon-free source of energy is putting nuclear energy back on the equation, back into the equation. And the notion here is that if that's the case, what are we going to do with all this SNF, which has been accumulating at the sites and hasn't been being transported to Yucca Mountain because of the institutional difficulties in making it happen? Harry Reid is the Senate Majority Leader. He's from Nevada. He doesn't think this is such a good idea. I'm guessing it's going to be very hard for it to happen in that political context. It's interesting that I've been able, in my class, to show the dynamicism of the way in which political structures change. I used the same case in the class for the first time last year. And last year I was able to make the statement that Harry Reid was the minority leader of the Senate, a powerful post, of course, but not as powerful as I can now project him as the majority leader, since the Senate, of course, changed, the control of the Senate changed in the 2006 election. So again, the dynamicism on the institutional sphere as well as the dynamicism in the physical sphere, as one thinks about technologies that might develop, are very interesting. So I think I'd like to stipulate that this is a complex system, both institutionally and physically. Certainly it's large scale, it's continent-wide and nationwide in the United States. It has large-scale impacts as well on a number of different people and a number of different constituencies. It is interconnected. The I in CLIOS, it connects with the energy system in the sense of this relating to the generation of energy in the U.S. and around the world. Currently, the United States generates about 20% of its electrical energy through nuclear power. The notion is plausibly this might grow. Certainly energy use is going to grow, so we may see more and more of this. And the relationship I just noted, that with global climate change is an important interconnection with another socio-technical system. It's not on this particular chart, but one also worries about the interconnection with the global political system, because one of the concerns that people have about nuclear energy, in addition to doing something with the spent nuclear fuel, is the question of proliferation. The same processes that generate electrical energy are are equally usable in generating weapons-grade nuclear materials, plutonium. And the issue of, for example, the development of nuclear energy in unstable states in developing and developed countries, which may lead to proliferation of nuclear weapons, is an important geopolitical question that one has to consider as well. It's an open system. We're concerned about social factors. Risk is fundamental to this. How do people perceive and actually absorb risk as one transport these systems? I've just mentioned political factors, geopolitics, and proliferation. Economic factors, development is key. We've known for centuries that the interconnection between energy use and GDP per capita and presumably economic quality of life is important. So the continued provision of energy is vital to economic growth and development. And finally, socio-technical. We're talking about transporting spent nuclear fuel. There's complex technology to deal with it in the transportation systems, in the management of the below-ground repository in Yucca Mountain, Nevada. There are important social impacts associated with this, as I've been highlighting. So this is an example of a CLIOS system. One could come up with any number of others as we proceed in the to discuss this in the context of transportation, although obviously in many other socio-technical contexts as well. And as promised, and I assure you this is the first and last you're going to see of the CLIOS process in this talk, we have developed a process for studying these CLIOS systems called the CLIOS process that takes people step by step through a representation, a design, evaluation, and selection, and an implementation stage in thinking through how one actually makes changes in these systems, in these engineering systems or CLIOS systems. And indeed, we are using this in this undergraduate class that I talked about. The students have finished the representation stage, that is trying to understand what makes the SNF system tick, and are now beginning to move into the design, evaluation, and selection stage. And in the last stage of the CLIOS process, something that is often not considered, at least in my view, adequately in many processes dealing with complex political and social issues, thinking through how one is actually going to deploy the strategic alternatives that one designs, both institutionally and physically. So thinking through the strategies for deployment, which clearly has been a failure here in Yucca Mountain. In 1987, the United States Congress passed, and the president, in those days Reagan, signed a bill saying we're going to move all this stuff to a geologically secure repository, and its name is Yucca Mountain. And we have a contract, both a technical contract and a moral contract with the energy generators to do so. And meanwhile, we haven't transported 1 ounce of spent nuclear fuel in the subsequent 20 years because the implementation has proven to be so overwhelmingly difficult. So I'm not sure my 15 engineering undergraduates are going to solve that, but I'm going to make them think about it and what needs to be done to think through the implementation phase of such a CLIOS. I'm going to skip driving factors just in the interest of time and making sure that we have adequate time for discussion. And let me move into my characterization of the evolution of the field. And I characterize transportation. I'd be very interested in people's views about whether they think I have this right or not. I characterize the field of transportation as evolving over the past half century or so through various eras. And I talk about the infrastructure era, the transportation systems era, and the transportation as CLIOS systems era, thinking more expansively about the idea of systems. And because people tend to personalize these these views, as do I. Basically, the infrastructure era goes back to when I was an engineering undergraduate at the City College of New York back in the late 1950s and early 1960s. The transportation systems era I personally associate with going to MIT in the mid-1960s as a graduate student and beginning to learn about systems and their application of transportation. And the transportation as CLIOS Systems Era is an early 21st century construction, again associated with the advent of the Engineering Systems Division at MIT and some of the broader thinking that I and other faculty and graduate students have been involved in. So while there's a continuum, I think, and other people might think of these eras as placed differently in time, at least for purposes of this discussion, think 1940s, 1950s for infrastructure when Joe Sussman was an undergraduate. Think about the 60s and 70s as transportation systems when Joe Sussman became a grad student and a wet behind the ears assistant professor. And now think of CLIOS systems as early 21st century as we move into this engineering systems division perspective at MIT. We could quibble about the time frames, but let me give you my perspective on these various eras and what they connote to me as one defines them. So I would characterize the infrastructure era as very much an engineering in the traditional sense era in the field of transportation. The idea was that transportation folks built what, quote, they want, where they might be the politicians or the perspective on what people thought the public wanted. So you had ideas like desire lines. You had origins and destinations, and you drew desire lines. People wanted to go from A to B. So what could be simpler than building some transportation infrastructure to take them from A to B? The focus was on physical facilities. When I was an undergraduate, we learned a lot about designing physical facilities. How thick should the pavement be and what material should it be made of? What should the super elevation of the highway be? And so on and so forth. Thinking in very physical terms about what we wanted to design. The focus was on mobility, that is, getting people from where they were to where they wanted to go at any time they wanted to do it in a relatively unencumbered, in principle, congestion-free way. So mobility was why we did these things. The focus was on economic growth. Building infrastructure was good for the economy. Mobility is good. We move people, we move freight. People get to better jobs. People get goods in the supermarket. We will grow economically, and that is indeed true. And that was the focus that I learned. And we tended to have largely a modal perspective. You were a rail person. You were a public transportation person. You were an air person. You thought in very modal terms about the transportation system. So a kinder, simpler era characterized by President Eisenhower in 1956 signing the Interstate Highway Act, a explicit highway system focusing on mobility and on the highway mode with very little, if any, consideration of any other modal approach. So now we fast forward into the mid-60s and the 1970s, and now we're starting to think more broadly about transportation as a system. So now we start to see the development of an economic-based framework for thinking about how the transportation enterprise should be designed. So we start thinking about mathematical constructs like supply functions. We start thinking about demand analysis, trying to understand how we can predict demands from origins to destinations based on economic principles. The paradigm of equilibrium, long part of the economics literature, starts to be explicitly considered in transportation. Well, we have a supply function, we have a demand function. The intersection of them will give you some prediction of what the actual volume will be on a particular facility. And we begin thinking in terms of networks. We begin thinking not about individual transportation links, but how they fit together in a network sense. So rather than thinking about a set of unconnected projects, we think about how networks will operate, and we're more concerned now about performance. There's that word again. We're more concerned about performance of networks than we are of individual facilities. We broaden in the transportation systems era to go beyond economic development. Economic development, of course, is important, but we go beyond that to now start thinking about environmental concerns. These big highways, these big airports, these big rail lines don't just tiptoe in. They have profound environmental impacts, perhaps on wetlands, perhaps as a result of investments made in highway transportation on air quality. We begin thinking about the environmental implications of the decisions we're making. I can't swear in a court of law on this, but I think when I was an undergraduate in the 50s studying civil engineering, that I'm not sure I heard the word environment. Certainly I didn't hear it in any transportation class. We build a damn highway and, build it straight and inexpensively, and let's not worry about a whole lot else. That no longer is extant, and wasn't extant for very more years beyond that time. Environmental concerns were on the agenda beginning in the systems era, which I characterize as beginning in the 60s. One can argue about that time frame. We focused not only on mobility, getting people where they wanted to go, but we began thinking about accessibility. And I mean accessibility here in the broad sense. I'm not simply talking about accessibility, for example, of elderly and handicapped to transportation. Of course, that's a critical issue, and indeed your trolley system here in Portland, which my wife and I rode yesterday, does, it seems to me, a particularly nice job of handling that kind of accessibility. Here I'm talking, in a sense, perhaps about capital A accessibility, the idea that one thinks not only of getting where you want to go very quickly, but also about what the destinations are about. What are the opportunities at those destinations? And accessibility means accessibility to schooling, accessibility to jobs, and can the transportation system get you to those kinds of opportunities? So if one thinks in terms of purely mobility, you can get a lot of mobility out there in the Badlands of Wyoming. There's not a lot of congestion out there on the intercity interstates in Wyoming, but the number of interesting destinations, you might think, are relatively modest, unless you're especially interested in jackrabbits or something like that. I better be a little careful about those characterizations. But the notion here of accessibility in an urban sense means that we have a lot of potential opportunities, a lot of job opportunities and so forth. And the connection of land use and transportation begins to be made more explicitly. We begin in the systems era to recognize the importance of unpriced, what I call unpriced externalities. That is, impacts that we cause by our transportation decisions that we don't, as individuals or as companies, pay for. So we have congestion, which one could argue results from unpriced externalities. That is, when I move into the traffic stream, I may pay a price as a result of it being a congested road and it takes me a long time to get to work, but I don't pay anything for the fact that I cause a diminution in your level of service with you already in the traffic stream, nor do you pay for the externality you cause on me. So the notion that unpriced externalities, things that are negative but nobody individually pays for, causing problems in the way in which we deploy transportation systems begins to dawn on us. So the notion of congestion, air quality, urban sprawl being something that no one pays for individually, so we all pay for collectively, but we have no policy knob to turn on it. And finally, in the systems era, we have an intermodal perspective, the idea that now we're no longer thinking about single modes, we're talking about interconnections between modes. Back in the 60s, that was probably largely a freight-oriented idea. That is, that you would have interconnections between rail and truck and ocean shipping and containers and things of that nature. Now, of course, we've moved into the intermodal era with respect to traveler transportation as well as freight transportation. But certainly the notion that one thought about a transportation system composed of interconnected modes became important in that period. And finally, so this is progress, but finally I suggest that we have now moved into a broader systems perspective, a complex, large-scale, interconnected, open that is CLIOS system perspective, and that the generation of transportation professionals that we're trying to educate now, we hope will have that perspective. And practicing professionals, we hope we can convince them that this is a valuable perspective as well. So how do we characterize the CLIOS systems era? We're thinking about certainly a field that is now much more characterized by advanced technology and advanced mathematics in studying how to design and how to enhance the operations of transportation systems. We've mentioned ITS several times in the course of today, and ITS is probably a good example of advanced technologies in communications, computation, sensing, and the like, as well as mathematics in the sense of advanced algorithms. This technology is having a profound impact on the way in which we operate transportation systems in a way that we haven't had before. It's characterized by institutional change, the idea that we are seeing new kinds of relationships developing, and those kinds of new relationships, after a long period of relatively static institutions, we are seeing some relative rethinks in terms of, for example, the relationship between the public and private sector. So new business models, new roles and responsibilities, institutionally speaking, is now on the table. We can no longer take, in CLIOS notation, we can no longer take the institutional sphere as fixed when we think about innovating in transportation. We have to think about changes that are occurring or that we might try to have occur on the institutional sphere as well. So I argue that's a second important characterization. The third relates to the I in CLIOS, the explicit notion that transportation is deeply interconnected with other socio-technical systems, that we are thinking quite explicitly about the connection between energy, the environment, economic development, social equity, and the transportation system. That transportation as a policy lever on a variety of dimensions, given those interconnections, is part of what I argue that we're in as we move to this CLIOS systems concern. We are seeing an expanded role for what I would call stakeholders and a broader definition of what we even mean by stakeholders. If I go back to the bad old days of the 50s, the idea was that we as transportation professionals knew what was good for the public, and what was good was a straight shot from here to there, wherever it took us, and the relationship of stakeholders, people who, for example, might be impacted in a negative way by a particular transportation decision, was largely off the table. We were the professionals. We knew what was appropriate. And now, of course, that's long since no longer been the case. We had the Embarcadero revolution in San Francisco, as people said, we don't really want this piece of urban infrastructure. This is a bad, not a good thing. We had the highway revolt in Massachusetts, where a previous, the governor of the state, Governor Frank Sargent, who had previously been the head of the highway department, came forth with the notion, based on research done in academia by people like Alan Altshuler and others, saying, we're not going to build any more highways inside of Route 128, the inner beltway, if you will, in Massachusetts, because of the concern that stakeholders have and because there are limits to how much highway infrastructure we can have and still retain a city of any viability. So the notion here is that stakeholders have an important role in thinking through what kinds of transportation systems that we ought to deploy, and we need to think very broadly about who those stakeholders are. Some of them may be largely disenfranchised or so diffuse as to have very little impact on decision makers. So the notion here is that involving stakeholders in all parts of the process is a fundamental precept of what we want to do in modern day transportation system design. I went through the CLIOS process at warp speed, but perhaps some of you paying particularly close attention noticed that the first phase was representation, which is the part of the process where one simply tries to characterize a complex system prior to even beginning to think about what one might do to enhance its performance. We've done some research at MIT. A doctoral student of mine named Ali Mostashari, who's now at the United Nations Development Program, did research at MIT that looked at the role of stakeholders in the representation phase of CLIOS systems. One can make an argument, and he did, and developed some empirical data to support it, that having stakeholders involved even before the decision-making begins to start, just trying to think about how you characterize the problem, has some value. It has some value subsequently in the development of strategic alternatives that are sensible. It certainly has value, as we've known for a long time, in that the early involvement of stakeholders will tend to ameliorate some of the institutional resistance that may occur down the road. And interestingly, it tends to lead to a better, a more accurate systems representation, to have stakeholders at the table simply while one thinks about what the issues are in the system that we have under consideration. So he, in fact, looked at not at a transportation application. He looked at a program called Cape Wind, which involves the building of a wind farm in Nantucket Sound off the coast of Cape Cod, an important and very affluent tourist area, and building a constituency, or not, depending on your perspective, for creating that renewable source of energy out in Nantucket Sound, and worked with stakeholders to contrast the representation they came up with of that complex system with that the Corps of Engineers came up with, and to understand the kinds of insights you can derive if you have a lot of different perspectives on the table. So this idea of stakeholders and their role throughout is very important. It's worth commenting, by the way, it's sort of a parallel to my spent nuclear fuel example, that stakeholders' views tend to change as time goes on and as their own interests are impacted in various ways. And I noted for the spent nuclear fuel issue that all of a sudden we have a lot of environmentalists who are very interested in nuclear fuel because of its modest or virtually zero carbon footprint. There's a similar case in Cape Wind, because Cape Cod is largely a resort community. I would characterize the mindset of many people on Cape Cod as highly environmentally oriented. They're very concerned about the environment, and they're very concerned about what tourism does to the environmental characteristics of the Cape. So certainly this is an environmentally sensitive community. Here we have a renewable source of energy that's being proposed to provide, as I recall the numbers, 2/3 of the power for the Cape itself, and the environmental community hates it. The environmental community says, this doesn't sound like such a good idea because I'm going to be standing there on my veranda having my martini one nice summer afternoon, and I'm going to be able to see these things out there in Nantucket Sound, and I don't think it's very good. So their stakeholder perspective, their environmental sensitivity, turns out to manifest itself in a quite different way than it might have in other kinds of decisions. So understanding that kind of dynamicism is important. We've seen some extraordinary studies about the numbers of bird kills that people project will occur when these windmills, and they are not unintrusive, I would say. These are big pieces of hardware. The numbers of birds that might be killed and by the presence of these things. But those numbers were contrasted in a way that I had no idea existed with the number of bird kills that occur in skyscrapers in Manhattan, and the numbers are comparable. I don't think anyone especially worried about that. So no cynicism here, but understanding the roles of stakeholders is important. And finally, we're talking about systems that are characterized by concern with what we call the ilities, kind of micro performance measures of these complex systems. The ilities is a term that was coined by Professor Joel Moses, the director of the Engineering Systems Division, and they are such things as durability, mobility, flexibility, and so on. The notion that we have to think about a broader set of performance characteristics for these complex socio-technical systems if we're really going to make the right kinds of design decisions. Now, it's 1 o'clock. I want to be sure that we leave plenty of time for discussion. I have various slides on each of these characteristics that go into the discussion in much more detail. And I think I'm just going to show the first of them, that is those concerned with advanced technology and mathematics, and I'll skip the rest. People who are interested in the PowerPoints, Rob, I guess these will be available. I have no problem with them being shared with anyone who's interested. But let me just say a few words about the mathematical perspective and technology perspective and the implications that it has for the way in which we deal with transportation system design. So we have a variety of advanced technologies. I mentioned some in the ITS context, but there are, of course, others. And advanced mathematics, operations research types of mathematics that have enabled a variety of ways of thinking about the transportation system that we haven't had at our disposal at least at the level that we have had before. So these new technologies, new mathematics, allows us to think more actively about an operations focus, not simply thinking about building and maintaining infrastructure, highway infrastructure in particular, but also how one effectively manages it by measuring, as the folks in the ITS lab were telling me, measuring traffic flows in real time and making judgments about how to more effectively operate the transportation network. We have the ability to tailor customer service. The idea that highways, perhaps, is another good example, don't have to be a one-size-fits-all kind of technology, but through pricing available through these technologies, we can provide customer service that will distinguish people on the basis of their willingness to pay. Now, I understand there are institutional questions associated and equity questions associated with it, but it does give an opportunity for thinking in new ways, congestion pricing, for example, about the way in which we provide transportation service. We have a very rich information environment. The notion here is one can do planning much more effectively. Intermodalism is very much enhanced by these advanced technologies, and we move into supply chain management for freight transportation in particular, enhanced by the ability to measure and monitor flows of goods on networks. Very large-scale optimization allows us to look at, for example, complex air networks and run them more efficiently. And in what will be the last slide, the idea of disaggregate demand modeling as a mathematical technique that allows us to understand what the demands for transportation service are, real-time network control and provision of traveler information, enhancing the performance of the system and enhancing the traveling experience. Vehicle automation, potentially. We see this in limited forms at airports and what have you. The idea of automating or partially automating vehicles, and the notion that we now think of traffic safety from a crash avoidance as opposed to a crash worthiness perspective, a fundamental shift in the way we think about safety. I've mentioned sophisticated pricing methods the technology enables, which allows us to enable the externalities, to price the externalities that I characterized as unpriced earlier, congestion pricing, environmental pricing, and the like. And finally, the notion of being able to look at transportation and operate transportation systems at a regional scale, a much broader geographic scale than we could before. And in some of my writings, I've advanced the notion that the region, typically the urban-based region, is an economic engine. And long since, the economists have talked about the regional scale as being the appropriate scale for studying economic competition, regions within nations. And the environmentalists have talked about, while global issues are important, managing the environment at the regional as opposed to the merely urban scale was critical. And now we finally have the technology to allow us to look at that scale for transportation operations and management. So in the CLIOS Systems Era, we have all these opportunities that have been enabled by what's going on in the world of technology and mathematics. And I could go on to discuss in comparable detail the other characteristics of the CLIOS Systems Era, but I wanted to assure that there was some time for interaction and questions and comments that people may have had. So I appreciate your attention, and I'm happy to try and respond to any points of view that people want to advance. So thanks so much. You can applaud. That's all right. Yes, sir. Yeah.
Yeah, I was wondering, in the process that you described for designing within a CLIOS system, I was wondering if there were any sort of specific deliberate strategies that you espoused for dealing with these sort of emergent, unplanned, unintended consequences that you alluded to very early in the process.
We've got a number of papers on that where we go into that in some detail, but just to give kind of a couple of headlines. Of course, the facile answer on that is if one thinks about the representation carefully enough, one will not have unanticipated consequences because of a deeper system understanding. We understand we're only human beings; we're not God, so we will have some of those arise. The strategies that we have focused on in thinking about these systems is first of all to make explicit the fact that there is uncertainty in the performance and in the external factors that will impact upon the system. So uncertainty and characterizing uncertainty is fundamental to what we're trying to do. This is not a deterministic world. It never has been, but it's certainly not in the case of the kinds of systems that we like to consider here. So the idea of flexibility in design is part and parcel of what we're trying to do, to come up with designs that will be flexible both physically and institutionally so as to be able to deal with these unanticipated occurrences when, I won't even say were they to happen, because in some sense they always happen. So we have students and colleagues who are studying issues and analysis methods. Are you familiar with the idea of real options analysis? Anybody know anything about real options analysis? The idea here is that one would like to design flexibility into a physical system to take care of what you were just describing. And flexibility is never free. That is, if you're going to design flexibility into the system, there are some costs associated with doing it. And the question is that flexibility worth what you are paying for it, given that there is some possibility you won't need it? That is, if you're designing flexibility because of uncertainties associated with future demand, and demand does not develop, you've created flexibility at a cost that is then never exercised. So the question is, how does one value that kind of flexibility? How does one put a numerical, a dollar value on it? And there's a lot of work that's gone on taking the mathematics and the approaches of financial options, which are a way of hedging against uncertainties in pricing in the price of securities in the future, and the Black-Scholes equations and all that kind of heavy-duty mathematics, and applying those approaches to real systems, hence the term real options, and using that as a frame of reference for understanding what the value is of a particular flexible system. So I have a doctoral student right now who's looking at flexibility in the context of ITS. He has two case studies in his thesis. One is dealing with flexibility in ITS systems. The other is dealing with flexibility in the design of aircraft and the blended wing body concept for Boeing. And his notion is that you have a technology like ITS and it has some inherent value. That is, presumably we deploy it because it's a smart thing to do. We can provide traveler information, we can reduce congestion, and so on and so forth. But his argument is that on top of the inherent value of the technology, we do it because it's smart to do it, that it also has some value inherent in the flexibility it provides. In the case of ITS, it may be a flexibility in terms of being able to delay the building of conventional infrastructure, which is very expensive and very permanent. And being able to delay that for some period has some value. It may have some value in the ability to switch between the ways in which we manage various lanes, special use lanes. So he's looking at trying to understand the flexibility value of that technology. So that's one of the approaches we've taken, a focus on uncertainty, a focus on flexibility, and properly valuing it as one strategy. There are others that we've talked about, but let me give some other people a chance. There was a question right behind me.
Can you tell us how the MIT team for the DARPA Urban Challenge is doing this year, and what are the implications in the CLIOS type thinking?
I can't. I'm not involved at all in that urban challenge question, and you perhaps could speak in a more articulate fashion about what's going on. But there have been rounds of competitions in which people have designed automated vehicles that run in the wide open spaces out in a desert somewhere. That's a challenging technical question in any case. Having an unmanned vehicle operate and sensing the environment and getting from here to there without crashing or running into something. The next level up is the idea of taking that same kind of concept but doing it in an urban area where you have other traffic, where you have impediments that may arise, pedestrians, what have you, and that's the next step. Now, that's about what I know about it. I can't really speak to the question of how the MIT team is proceeding. Perhaps if there's anything you can add to the discussion, you are welcome to do it. Sorry, I can't talk about it. I know we're involved, and the question of automation is one that's on the table and a very potentially a vital piece of the equation, although there are many skeptics, and I would have to candidly put myself among the skeptics in terms of automated transportation. A piece of ITS is something called AHS, or the Automated Highway System, and the idea of AHS, which is now largely defunct, except as a research topic, was rather than simply monitoring flows on transportation networks and providing traveler information and changing lane use and speed limits and finding accidents in real time. The idea of AHS was kind of exactly what it sounds like, the idea of automobiles running in automated fashion on specially equipped guideways with an electronic interconnection between the vehicles and the highways and between the vehicles themselves. And the notion was these vehicles would run in platoons, very closely spaced platoons of vehicles at highway speed. And the theory was they take the driver, presumably the least safe component of the highway transportation system, driver error being the cause of a large fraction of accidents. By taking the driver out of the loop, one would experience very large capacity improvements, because now the cars could run a meter apart, since you don't have to worry about how fast a human being is going to hit the brake. So the notion here was this is something that could have important impacts. But while the technology has been demonstrated, in fact, back in 1997, I went to an ITS conference out in San Diego, I think it was, where the technology was demonstrated. But there is little sense that just because this technology exists and can be made to work, that it makes a lot of sense to actually do it, that the costs and benefits may be very far out of whack. And the question of whether the safety enhancements would in fact occur is something that is debated in the community. So this is an example in which the technology, I talked about technology and the potential impacts they can have, but technologies also have to pass some standard of relevance and cost-benefit at some level of analysis if they are going to be implemented. We shall see. Rob Bertini, Professor Bertini, of course, was a student before he came here out at Berkeley, and Berkeley has, out at the PATH program, been a strong advocate of automation and AHS. And I suspect you might get a different view from some of the researchers at PATH from that you just heard from me. But largely, the notion has been that those systems have not moved forward. Other questions? Yes, Jill.
Obviously, this has implications for engineering education and curriculum, and it sounds like at MIT your curriculum has evolved to focus more on sort of some of these broader issues.
Yes.
I wonder if you have a sense of change at other places and whether or not other engineering curriculums are sort of moving in this direction. And then perhaps more broadly, I'm really interested in sort of this issue of trying to get more students interested in transportation as a career, because we're facing sort of shortages, and how you think sort of this way of thinking might be more or less attractive, or how that might, what are the implications for getting more students into transportation?
There are a lot of questions inherent in that sentence. I think I stopped counting at 6, so I'm not sure I have all of them. But first of all, from the point of view of other academic institutions beginning to think more systemically, I think the answer is they are. There are schools that have been in the forefront of that kind of movement. MIT, I'm proud to say, is one. Carnegie Mellon is another. Berkeley has been affected. Texas has been effective in this area, but it's a long and slow pull. And there are some demographic factors involved in this as well. The demography, in this case, of the faculty of engineering schools. And in this era of no fixed retirement age, the turnover in faculties tends to be more modest. When I joined the MIT faculty 40 years ago, the notion was that one could expect that with a mandatory retirement age back then at the age of 65, that people would leave, and there would be some renewal that would that would take place that might reflect different thinking. But that, I don't remember exactly when that went away, but it went away. And people like me are now at MIT beyond the age of 65. So the rate at which faculties can renew themselves and bring some of these ideas into the intellectual marketplace is to a certain extent limited. I believe that the kinds of things that we're pushing here, the idea of transportation as a special example of large-scale complex systems, CLIOS systems, is something that has some connection, because people can think about learning the concepts associated with this and connecting or interconnecting, to use the I in CLIOS, with other kinds of domains. And energy and the environment are two obvious ones. So the notion of there being a broader intellectual field of play, I think, should be attractive to students. We've long gone beyond the question, at least at MIT and a lot of other places as well, we've gone way beyond the issue of the focus on physical design. And that's not to say that physical design isn't important. One has to get the pavement thickness right if one is going to have a highway that is going to be sustained over a period of time. But one has to have the academic institution focused on the non-routinized part of the profession. We know how to do those kinds of things. And what we need to teach our students are what we know much less well, that will be the cutting edge of what goes on in the profession, not the day they graduate, but rather 10 or 20 years out when these people are in senior positions. So there's a certain amount of selling that has to take place to the consulting community, to be perfectly direct about it, and the state DOTs and organizations of this sort, who have, to me and to my colleagues, often criticized our graduates, not on the basis of their intellectual horsepower, because we're blessed with having a large number of very good students, but they've been criticized by not being 100% billable on day one. We want to hire your student. They're going to walk down the aisle and graduate in the Killian Court on June the 6th. Then they're going to take a week off to catch their breath, and on June the 15th they're going to come to work with me, and I want them to be 100% billable. And that's not the goal in our educational construct. Our educational construct is to think about educating the leaders of the future, and to recognize that a certain amount of education is the responsibility of the consulting community, not simply the responsibility of academia. And indeed, my view is that if we educate people that are 100% billable on day one because they know all the routine stuff, we're doing both those people and their firms a strategic disservice, because who's going to be running that firm in 10 years? And is it going to be somebody who is real good at picking pavement thickness? Well, I'm thinking not. So it's a tough sell, but one that we continue to try to make. The idea of making the practice of transportation more attractive, I think, has an upward thrust resulting from some of the change in the business models in transportation system operations. And the idea that there will be a much stronger private sector footprint in the provision of infrastructure, the operations of transportation systems, thinking more broadly about what the private sector role will be. So having folks limited to simply public sector trajectories, and there's nothing wrong with public sector trajectories. The public sector obviously has and will continue to play a vital role. But the fact that students now have potentially a track in the private for-profit element of the transportation field is something that I think makes it more attractive as well. Okay, I answered 3 of them. You had about 4 others I can't remember, but we'll get them off. We'll get them offline. Other questions? Yeah, in the back.
aggregate demand analysis, capital demand modeling. And so one of the problems is...
So you're in the black magic section of our profession.
Exactly.
I find it extraordinarily interesting how more effective we've come in that area with some of this mathematics. But some of it is black magic.
Don't tell them. But so...
Is your advisor here? No, I would be careful.
Yeah. My advisor got his PhD at MIT. So, so in that area, we can conceive of a lot of very advanced models for modeling individual behavior, and we can come up with some integrated land use and transport models that also include regional economic models. So in this sort of spirit of complex systems, we're moving in that direction.
Right.
We're moving away from the deterministic models of flow allocation to ones that are based usually on Monte Carlo simulation where there's a lot of uncertainty. So the problem with all this is it's really hard to communicate these types of models to decision makers. They don't want to see a distribution of outcomes. They don't even want to hear that there's a distribution of inputs. They want a point estimate. Right? They want to know this is what my transit share is going to be in the year 2030. Don't tell me that there's this range of possible futures. So have you and your colleagues done any work in trying to sort of reduce problems or communicate them in a way that can be understood by decision makers?
There's been a lot of thinking about that and a lot of work on that, but I think it's very much a work in progress. There's a reason that those decision makers don't want to hear about distributions, and it's not simply that they can't understand it, because they can. It's because within the political structure, determinism is highly valued as one goes to the funding agencies, as one goes to the federal government, for example, and looks for support. So that perspective is the antithesis of the point I was making in response, I think, to the very first question about the need for thinking flexibly about the transportation system. It's interesting to me that while we as transportation professionals value the idea of creating a real option, a flexible system that can respond to uncertainty, a lot of people in the political domain view it precisely the opposite. So we had, I'm suspecting people here know about the Big Dig in Boston. It's a pretty much a national story, and it has greatly enhanced surface transportation in the Boston area at the modest price tag of $14 billion. So we think we got a pretty good deal, but whether you think it was for the fraction of your taxes that was directed to that infrastructure investment is a different question. So that all the work on the Big Dig, which went on for a 30-year period, including the political process and what have you, preceded all of this focus on flexibility. But we've had discussions with some of the decision makers about flexibility in terms of characterizing that project and going to the political process and talking about the need for flexible approaches given the distributions that you've discussed, and the more candid of the decision makers have said, frankly, the last thing we want is flexibility in these systems. That's the last thing we want. It's hard enough to cobble together a coalition to move forward on a large-scale infrastructure project without 5 years in saying, we designed this flexibility into the system. Now it's 5 years later, and lo and behold, the environment is such that we ought to utilize that flexibility. We ought to change the design. And their perspective is, this isn't a good thing. This is a bad thing, because that flexibility means we have to reconstitute this constituency, which took blood, sweat, and tears to hold together. So once this project is in motion, we're not looking to the left or the right. We're going to get it done. And real options and flexibility is the last thing that people want to think about. So the notion of of characterizing this to the political structure, if they're telling you I can't understand it, I think they're blowing smoke. I think they understand it perfectly, but it's not in their interest to think about probability density functions. It's in their interest to think about point estimates and going to the bank and getting the money. Certainly, in some cases, you get into some highly technical questions. In our work in Mexico City on air quality, there are some pretty technical questions you have to deal with in terms of compositions of fuels and how they will relate to what happens to what comes out of the tailpipe and how that relates to what happens to the environment and so on and so forth. So in some cases, there are very difficult technical questions, and working on ways to explain those to decision makers is an art in and of themselves. But in the case that you just described, I think it's more of a willfulness not to hear about the fact that these are probabilistic systems, because there's the natural question of what if demand really is much lower? You're at the left-hand tail, not the right-hand tail. Why are we doing this? And given the extraordinarily poor record of predicting such things as volumes on transit systems, one has to start to wonder whether our profession is systematically and politically predicting those demands much too high. That is, we're simply not making mistakes in our disaggregate demand modeling. It's in our professional interest for those demands to be predicted at the high end of the scale, because that's what our client wants to hear. It's a very difficult kind of a question. I see the hook coming up here, so I think I'm done.
So yes, thank you. Before we thank our speaker, next week I hope you'll join us. I'll be leading a presentation, kind of an update of our regional transportation archive system called Portal. So you'll be stuck with listening to me talk next week, and hopefully some of our students on that the team. So let's thank Professor Sussman for his presentation.
Thank you.